Just very briefly, a few words about nVent, because may some of you know the Schroff brand, may some of you know Logic. So nVent is a global company. We are US based, so we do around $3 billion sales globally. Nevertheless, you can see from the small split here, about 20%, 25% is in Europe. And then we have the enclosure business, and that's why Ulf is here, Ramki is here, myself is here. The enclosure business is what we call the Logic, the Schroff, and the Hoffman brand. And I jumped over this. I think that's just important for you to know. If you run into these requests, I think being part of a global company, the advantage is that we are well prepared when it comes to quality certifications, when it comes to ESG activities. So we can, besides the products, we can also cover this activity if one of your customers, or if you basically require those documents, we have them already. And then, as said, it's just an introduction to frame a little bit ourselves, to frame a little bit the company before handing over. That's what we call the solutions for data centers, white space, but as you see in the introduction, also edge applications, or basically decentral data protection, what you can also call it. So we have the racks, we have the power distribution, we have some additional monitoring and access control systems. Then we got wireways, we got grounding and bounding protection. We got leak detection, heat tracing in our portfolio, and the nVent portfolio, I have to say. And then, of course, we're going to talk a little bit more about cooling, not that much about containment, but the high-end cooling, the innovations and market drivers. Just two remarks on the power. I know we talk data centers mainly today. Our experience is, so two edits on that. We see also a demand when it comes to decentral installations. So when I'm not talking edge installations, taking an example, we have a big medical customer building big medical machines, and he's also using intelligent PDUs. And the reason is very simple: remote maintenance. So everything that goes decentral, there's also a chance to add these PDUs. Either it's switching, so that's normally the first thing when you ask IT, what can be done? Reboot. Or looking at power consumption of devices remotely, and it's much cheaper to invest this money at the beginning than sending all the time a service technician on site, which is basically taking off and plugging in the device. So just as a remark. And then the second thing, of course, the PDU and the feature and everything fits best into one of our racks. just a side note. Okay, let's talk about cooling, data center cooling. I'm in front here. I have the nice backup of Ulf. So every question I'm not able to answer, Ulf will get in. But first, looking a little bit about what is happening on the data center side. Just a few things we see. One important thing for me, at least what I know, is uptime. Cooling is critical, uptime is key, building in redundancies. Still a main thing. And then CapEx versus OpEx. Initial invest and total cost of ownership. So we'll try to touch this a little bit. And then, of course, the density, especially in data centers, that's something we see over the last years. Density per rack is rising. So it can be a driver, maybe stepping a little bit away of what we call traditional data center cooling. Download versus upload world, I briefly mentioned it. Decentral installation, putting standard server hardware, putting IT hardware, decentral to have short latency times and the computing power where it's needed. So this can also be considered when it comes to cooling. And then, of course, the last topic, sustainability. Cooling is still taking a lot of power when it comes to the overall power consumption of a facility. So there are ways on optimizing the power consumption, and this also relates to different cooling technologies. This is an overview. In the past, we call it the continuum of cooling. Today, I will focus mainly on some new ways of cooling, but taking uptime, taking initial invest into consideration, I would say still all of these cooling solutions, they have a place on the market. We do racks more than 50 years, so we are quite experienced when it comes to fan cooling, AC units, more in the industrial space. Then we move up aisle containment. And there was a trend that at least I see, when I look back 10 years, I was everywhere talking about aisle containment, air management, and we went in a raw level of cooling, let's say. So first here, perforated door, room-based cooling, raw-based cooling. Then we extended it with in-row cooling. And what is happening at the moment is we go from the room to the raw to the rack, and then even in the server. So aisle containment, integrated heat exchangers, in-row cooling, rear door cooling, direct-to-chip cooling, immersion cooling. And then what I added is, and we will touch on that, is the temperatures. And that's mainly for ESG, mainly for the power savings, free cooling. The closer you come to the processor, to the IT itself, the higher your water inlet temperatures on the cooling side can be. So that's a main driver. So, but let's have a look. And again, it's the same thing. If I'm too quick, just raise your hand and say slow down. But first, let's have a look at what I would say it's traditional way of data center cooling. Aisle containment. Already mentioned. What is the secret on aisle containment? Very simple, air management. Separate cold and hot air. And then you can do cold aisle containment, you can do a hot aisle containment. By separating the airflows, you get more efficient. I would say still a valid way of cooling data centers. The challenge I see is, I'm not sure if everyone or someone been in a data center with 10 kilowatts per rack, which is completely air cooled. So there is massive airflow already. Highly perforated floor tiles, a lot of air volume that you have to move. And I think that's the barrier, because basically the aisle containment is a great thing. What you do is you add some mechanical parts, doors, top covers, and you have an efficient way of cooling. All the technologies, all the components you need, they are available. So if you are not exceeding, I would say, 6 kilowatt per rack, aisle containment, considering initial investment and operating costs, can still be a good way of data center cooling. Then we bring the cooling device into the aisle containment using an in-row. We get closer to the heat, which also allow us to fine-tune a little bit the inlet temperatures. Nevertheless, I would say we also have limitations on the density per rack. The 25 to 30 would already be like a one-to-one relation, meaning you have a rack and you have an in-row. You have a rack and you have an in-row. Therefore, I would say the in-row cooling maybe makes sense if you go up 10 kilowatt, 15 kilowatt, in that range. The in-row cooling makes sense. And you can also already start thinking of increasing slightly your water inlet temperature. Then a little bit promotion, what we offer, and I want to point out one thing. So we have a device which can be configured as a closed loop system, meaning you are acting room independent. You have plain doors front and rear, and you contain the cold and the hot side within this small cube here. Or you go the traditional way, perforated door, you have a front to back airflow and in-row cooling devices in combination with an aisle containment. But what I want to say here is the relation. So we can perform and we can say our device is getting close to 50 kilowatt performance. Yes, with 14 degrees cold water. If we raise the water temperature to 20, we are in a range of 36, 35 kilowatt performance. If we even raise it higher, the performance is also going down. So that's something that needs to be considered on the in-row cooling. And then of course we have also standard interfaces on our devices, meaning Modbus RTU, SNMP, web interface, so for connection into the facility, just as a side note. What makes this different? This is a new device, so I was asked by product management to promote it heavily today. We came up with a very powerful device, so we optimized the position of the coil, and it's all hot swap, meaning even the power supplies, we have the option of 3 power supplies, and they are like comparable to OCP devices where you just slide them out and slide them in during operation. The same with the controller. You can slide the controller out during operation and slide it in again. So I think that's the main benefits on our in-row cooling device. Then going up the next, what we call rear door cooling. This means we put the heat exchanger on the rear side of the rack. So we take off the rear door and then we attach the frame with the cooling unit. And here there is, I think, it's quite simple. So my background is not engineering, but how I would say the optimizing the performance of a heat exchanger is first flow, and the other thing is the design of the coil, the design of the heat exchanger. And that's the benefit we leverage here. We have the whole space of the rear door or the rear side of the rack for the heat exchanger. When coming to an in-row, we have to turn it inside the device and we have to see that we get most of the surface used. This means with the rear door we can go up on the density, we go down to the rack, and we can also increase again slightly the temperature of the inlet because we contain the warm air on the rear side, so we can gain a little bit on efficiency. What I figured out is the rear door heavily relates to the size of the rack. So if you use a small rack, 42U, 600 wide, of course the surface of the heat exchanger is getting also smaller. And then it's difficult. Then you can come into comparison with in-row and rear door, and you have to really look at it. When you come to a 220, so 48 or 47 rack unit height cabinet with 800 wide, then definitely the rear door is a very, very good option. So just looking how we do it, we designed the whole solution in a frame, and this frame can be attached to an existing rack or it can be attached to another rack, meaning we take the cooling out of the rack. The rear side of the rack is still available for power distribution and data cabling. And then we offer 2 options in this mounting frame. One is what we call passive, meaning it's just the coil and the fans of the equipment are moving the air, or an active one which have additional fans on top. So the passive, very simple, can be used if you have a server cluster mainly, when you have similar servers all the way in the rack, because then you can calculate the air volume and everything, and you know if the IT equipment is able to overcome the pressure drop of the coil. If you can't do this, if you're changing servers, if you are changing equipment, if you have heterogeneous equipment, then we heavily recommend to use the fan package. And our fans only start turning if the differential pressure inside-outside is getting too high. So we measure this. You can also regulate by temperatures, but we suggest fan regulation by differential pressure, water flow regulation by temperature set points. Simple PED control, you set, you monitor, and then the device reacts. That's just an example. That's a case study where we installed 65 doors in an existing data center. And the challenge was they had the room-based cooling solution. They wanted to increase the water temperature to 18 degrees. They come in a range of 12 to 16 kilowatts per rack. And as of now, we are operating the data center quite successfully within these settings. Questions so far? Okay. Then, I have no idea where I am with time. Getting a little bit in the area now where we see first installation, but it's not heavily adopted. Liquid cooling in two ways. Direct to chip and immersion. And basically, just the question, why should we do that? And I think it's two drivers, basically. The first driver is new server generations. They are getting more and more and more powerful. So at one point, they will just cross the limit of air cooling. So we come back to the example of the aisle containment, where the volume of air that you have to push through such a server, it's not possible anymore. So they have the server vendors stepping away. And of course, this is happening step by step. First installations was mainly high-performance computing clusters. But now we see more and more coming also for graphic-intense applications. So there is a lot of companies having their data center and their design teams, they get an issue because they get the hardware air-cooled. So they are forced to go into the direction of liquid cooling. So that's the server side. And then there is, from my point of view, there is also the environmental side. As we can follow the logic, going closer to the heat, we can optimize the temperature, we can use free cooling, and we will come to that. It's always more efficient to operate a pump than operate a fan. So that's the environmental impact. So what I have here is just an overview on how we see the market. It doesn't mean that we can support anything, but I think it's just important just to summarize a little bit. When it comes to liquid cooling, we see two different ways. First is, I mentioned the cold plate, and then the second is immersion. Cold plate means you put a device basically on, or that's how the most vendors do it at the moment, you put on top of the CPU or the GPU. So inside the server where most of the heat is produced, you take off the heat sink, you put in a device, and the liquid is flowing around on that area. You can extend it to memory and other devices in the server. So the most devices or components inside the equipment is cooled by liquid, the better it is, of course. But you get to a challenge. Then you can use a single phase liquid or dual phase liquid. What is the difference? Single phase means it's normally water with some inserts or stuff, or you can have even a dielectric, but we don't like dielectric. The heat carrying capacity is much lower than water. So nevertheless, you go in with the liquid is taking away the heat from the processor, and it takes it out of the server. In the dual phase, you have a cooling medium which is changing. So when it gets warm, it evaporates. So it's changing from liquid to gas. But the principle is quite the same. You bring it in, it's taking off the heat, and it's leaving the equipment. Then looking at immersion. Immersion means we take the equipment and we pull it or throw it completely into a cooling medium. Here as well, you can have two different ways. One would be a tank, meaning you have, looks like a big fridge. That's always how it reminds me, where you just have it filled with liquid and then you put in the service. This also works with a dual phase or single phase liquid. And then there is another approach, what we call chassis level precision immersion cooling. Meaning you're not taking the server and you put it in a bath. You're taking the server and you put it in every single server in a small bath. I will come to that. And here we are on single phase, not dual phase cooling medium. What we focus is single phase cold plate, single phase immersion. I briefly described it, so putting the equipment in a chassis or having a cold plate at the server. Here we work with partner companies. At the beginning I mentioned nVent is a global company, so we invested in two partners in that space. That's why they are a little bit left and right. And then I think in the middle is what we provide as an infrastructure. And I will come a little bit to the layouts. So starting with a typical direct-to-chip layout, we call it a primary and a secondary site. On the primary side is the facility, is your dry cooler, is all the pumps, is everything. And on the secondary side, you have the server with the cold plate and then a manifold which distributes the liquid into the server. And then we are also using a so-called coolant distribution unit. The coolant distribution unit basically is having a heat exchanger. So they are separated physically, two circuits separated from each other. In this cooling distribution unit, we get the heat transferred to the facility, basically from the server cycle to the facility, and then also these coolant distribution units, they take care of the liquid flow. So it's also pumps included in that units. And then you can use different designs, you can scale it. We have units which are built for like 1 up to 3 racks, which is 19-inch rack mount, so everything is inside. It's 3 pumps inside, 2 is running in parallel, 1 is the backup, then the heat exchanger is inside, and we reach a capacity of around 40 to 100 kilowatts of liquid cooling. Then there is what we call a standalone CDU unit. So the footprint is like a server rack from the dimensions, approximately 800 wide, 1,200 deep. And then this unit contains also pumps, control, and all the connection, and is built to support up to 800 kilowatts of liquid cooling in a data center space. And then you just connect the manifolds, the cold plates in the racks, and you can scale accordingly as the controller in the unit is regulating flow and temperature. There is one important thing on direct to chip, you can't get 100% rid of air cooling. You always have, you always need an air loop as well. So this varies in between the different servers or the different equipment used, but as said at the beginning, normally the cold plate is on the CPU, on the GPU, in some systems on the memory as well, but you still have power supply and other small components inside which still produce heat. What we take as a rule of thumb at the moment is 80% cooling with liquid, 20% with air. And this means, considering direct to chip, you have primary circuit, secondary circuit, and an air loop. While this air loop can be done with different systems, you can continue, we mentioned this at the beginning, you can continue using an air containment system because we only talk 20% of the heat. So take the air, cool the air with an air containment layout and then add direct to chip in this layout as well. Of course, I like rear doors, so I took an example with rear doors. What we call a hybrid loop or hybrid cooling system. So what we do, we take 20 degrees from the facility, we go in the rear door. Of course, the rear door cannot cool the room lower than the 20 degrees coming from the facility. So what we have on the air side, 25 degrees, this is the room temperature. And then 33 inside the rack on the hot side, getting into the rear door. I think that's quite acceptable. As of today, 25 room temperature, 33 on the hot side. Then we have a return liquid of 24 degrees from the rear door, and we feed the coolant distribution unit. The cooling distribution unit is approaching the cold plates with 40 degrees and is having a return of 60, which then, with the heat exchanger here, gives us a return to the facility of close to 39 degrees. So that's just an example. It can be calculated based on the asset on different values. First, how much have to be cooled by air, how much by liquid, what is the acceptable temperature ranges in the facility, and then of course what is the size of the rear door, what is the size of the rack, and then also what is the coolant distribution unit, the CDU, used in that system. Just giving you an example how it looks like. That's a hybrid installation, 9 racks. Of course, you have a little bit more advanced technical room, so you need to consider a little bit more pipe work going in that direction. Potentially, you have a lot of stainless steel pipe work, so our manifold as well is based on stainless steel. You have to be careful on not mixing too much the materials in your pipe work. And then here we use the rack mount. We use the standalone CDU. We had the pipe work underneath the racks, getting in with all the control wave connectors. The server, which had 2 cold plates each rack unit, meaning we had 2 manifolds, left and right. And in this installation, we went up to 80 kilowatts total load per rack, meaning we also had to consider how do we mount the PDUs, because they use 2 times 63 amp 3-phase PDUs in that layout. What we did, and feels a little bit like extending the rack, so we used 1,400 deep racks, and we added an additional frame with our rear door on top. So the total system was close to 170 in depths. But it works, and as of now, this is 3 years in operation. Customers quite happy. And then the last, and I mentioned it, is immersion. So here we really go 100% liquid. What is chassis-based precision immersion cooling? We take a standard server, we take off the fans, we take off the heat things, and we put the 19-inch server in a 21-inch chassis. Then we add components. This is just comparable to a manifold. So it's nothing electrical, it's nothing really high rocket science. We just take pipe works because we bring the liquid here on the rear side. There is dual pumps. We transfer the liquid to the hottest places of the server. That's what we do here. And then we don't fill the chassis 100%. It's only filled to 1/3. So how can you imagine such a system looks like? You have the 21-inch chassis, you have a board inside from the server, and then just around the board there is liquid. And the pumps bring the liquid on top of the CPU, of the GPU, and then it drops like a waterfall down. And this means the cold liquid is coming to the hottest places and then is moving on the bottom in the chassis back to the pump, getting cooled by a heat exchanger on the rear side and transferred back to the hot place, to the hottest place. And here, of course, we use special engineered fluids, dielectric. And why we see an advantage on chassis immersion is you use standard rack layouts. So if you consider a tank, it's quite difficult. If you have a tank with dual phase liquid and you open it up, it starts evaporating in the room, so you have to regularly refill. If you don't use a dual phase liquid, use single phase liquid, it's getting oily. So this means if you want to maintain the server, you need a kind of server lift. To slowly take it off, you have to leave it a little bit dry, otherwise you make your floor mess, and then you have to put it back again. If you do it too quickly, you have like a wave, and then at the end of the tank, your floor is a mess as well. So here you don't have this, and we scale upwards. So we use a 2-meter or 220-meter high rack, and this means we can bring in 6 to 7 times more density in a square meter white space than compared to a tank, because we go upwards. You pull out the chassis, you take off the lid, and you can immediately work on your server, maintain it, you close the lid, and you pull it in again. That's the advantage we see on that solution, and we use much less engineered fluid than compared to a tank. Good. That's it. So, questions? Coffee.